Which is the most pink? A lovely activity, a lovely question. During the presentation today, there's going to be a few, not many, but a few maths questions you may want to pause, you may want to have a go at on a piece of paper with a pen. You may want to look at the question and perhaps go to your own schemes of learning and see, is that something that can be added? But I do encourage that this isn't just a presentation to watch from beginning to end with no pausing. Today I'm going to be talking about fluency and structure. What does it mean to be a mathematician? How would you define mathematical fluency? You may want to write down your answer to this. I did. Unlike the language we use in mathematics, such as prime number, factor, the language associated with teaching mathematics or teaching in general lacks the same rigour. Quite often words are used and they're not fully defined. Mathematical fluency seems to mean different things to different people. And this is a shame because mathematical fluency is directly mentioned in the national curriculum. So in today's session I want to try and share what different people might think mathematical fluency means and perhaps home in on a more robust definition, definitely saying what things it is not and perhaps coming closer to what it is. Some of our first responses have come from a response to a Twitter feed. Fluency means that students know their times tables and are able to quickly and accurately use standard methods. And I don't think any of us could argue that mathematically fluent students or people would be able to do those things, but is that everything? Another response was just a demonstration, and certainly whoever did this is fluent in doing a multiplication. They're accurate, it seems to work, but again, I think there's more to it than that. This person says fluency is mainly about number, being able to do the 4 operations and working with things like fractions, place value and decimals. Fluency is mainly developed in primary school. Again, there are aspects of that I can't disagree with, and some of the research does show that students who we commonly would describe as being mathematically fluent do have those first stages made in primary school, and they can obviously certainly do those things. But is that everything, or is there more to fluency than that? I quite like this one. Fluency is the point at which one no longer has to attend in order to perform. Not a kind of definition we would ever have in maths, but I wonder if it was a non-mathematician who wrote this one, but I think there is something quite perceptive there. Fluency in a subject like a language or music is far less subjective. It's interesting that the way you become fluent in a subject like music is often open to far less variation. Maybe for learning an instrument, practice and being engaged in the instrument you're trying to learn is key to being fluent. Maybe trying to apply learnt skills in a variety of situations or genres. The idea of practice, 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 and then you become fluent. Maybe music and maths lessons should not take such a radically different format if fluency is something we look for in both. But if you observe a maths lesson and a music lesson, they often do seem worlds apart. Fluency is about knowing how to solve problems without depending on rote memorization or standard algorithms. Over the years, many students have come to mind who've done very well at GCSE maths, but then really struggle at A-level maths. Some of these students are very good at learning GCSE content, learning the algorithms, doing past papers, being able to apply the things that they've seen from other papers, and there is an awful lot of repetition in GCSE maths. But when you give them something they've never seen before, they really, really struggle. The idea of being able to solve problems without having done rote memorization, I think that does make very strong mathematicians. And it also poses the question, how often in maths do we teach a method, process, or maybe an algorithm, we apply it for a bit, but then we move on before all students are fluent. And then we come back to that situation where lots of students have forgotten how to do it, and we need to almost reteach it again. I know a lot of the teaching for mastery kind of philosophy does aim at spending longer on a topic so that students become fluent, and then if a student is fluent, they have understanding, so they don't forget as easily. Becomes fluent in a technique, procedure, idea, concept, or fact at the point at which they no longer need give attention. I think we all experience this quite a lot when we think about algebra and how a teacher or a very able student seamlessly is able to go through question after question, page after page of algebra using complex techniques, and it doesn't stop them at all. Whereas a student who doesn't have the basic rules of algebra with complete fluency, they can't tackle problems. They can't look at a bigger problem and use that algebra to solve. It's too much of a big stumbling block. And the same is said for number work. If you're not confident in your use of number, you can't solve problems which require that. So this is by far my favoured definition so far. It's that idea that you do it seamlessly. And you could imagine this being the same for any subject, maybe in music, being able to just open the book and play the notes because you don't need to give that attention anymore. But that is the kind of fluency in many maths questions that we need our students to be able to do, to be able to see a question and just do it, see another question and just do it. It doesn't require them to have to think too much. I'm sure you don't need me to pause the video for this, but a fluent mathematician would be able to get the answer to this very quickly and seamlessly. A less fluent student would probably count the matches to make sure that it's correct. Mathematical fluency goes beyond just number work and being able to know multiplication facts. It's about thinking and the way you think. Another example where if a student is fluent, they'll be able to do this very, very simply. If a student is not fluent, they may do a column subtraction or something to that effect. And that's the idea that this fluency does need to be taught. We need to draw those number lines at some point. Maybe it's been done at primary school, maybe it's secure, and show students that we're jumping, we're moving up a number line and making those little steps along the way. Here's another example. You may want to pause and think how you would do it or how you would encourage students to do it. In my experience, many students would kind of do a long division, especially coming from year 6 to year 7. And they wouldn't spot the idea that if I just halve both numbers, then we have a much easier division to do. Perhaps even writing it as a fraction, simplifying the fraction. But again, I think you would have to be mathematically fluent to be able to have the confidence to do something like that. Somebody who can just perform algorithms, maybe the fluency isn't there, and that fluency does need to be taught and it needs to be practiced. Again, you may want to pause and think about this. Sometimes the definitions are the thing that aren't fluent. What does it mean to be regular? What does it mean about the sides? What does it mean about the angles? And additional language is sometimes useful. In this case, it is equilateral, but it is not regular. Perhaps a more abstract example. I had to think about this one for quite a lot, and it is quite controversial, and I'm happy for people to hold their own view on it, but I wouldn't define this as a shape, so I think there's an error in the definition. But if you actually are constructing this, you do turn through the same angle each time as you move through, so the sides are the same length, the angles are the same length. But again, it's a little bit controversial, and questions like that are good, but definitions can be a major stumbling block, and I've done this to kind of demonstrate that also it's not just about number. In the shape and geometry elements, having really good knowledge of definitions and understanding what shapes are and what words mean is absolutely fundamental for somebody to be fluent. The national curriculum, although it doesn't define fluency, it does give examples of what it means in the context by which it's written. So students can solve problems by applying their mathematics to a variety of routine and non-routine problems with increasing sophistication, including breaking down problems into a series of simpler steps and persevering in seeking solutions. Some of the language here, I think, we would really think is akin to fluency: persevering in seeking solutions, breaking down problems into simpler steps, and the idea of increasing sophistication. Pupils are expected to be able to reason mathematically by following a line of inquiry, conjecturing relationships and generalizations, and developing an argument, justification or proof using mathematical language. And the point where it's actually mentioned is to become fluent in the fundamentals of mathematics, including through varied and frequent practice with increasingly complex problems over time, so that pupils develop conceptual understanding and the ability to recall and apply their knowledge rapidly and accurately. Conceptual understanding as well as the recall and apply. And I think we often put recall and apply for the majority of our students, and then for our very best we put under that kind of hat that they can have conceptual understanding. But really, for all pupils, conceptual understanding is an expectation. So why do students need to become fluent? I'm going to make two quotes here. According to Dowker in 1992, to the person without number sense, arithmetic and algebra is a bewildering territory in which any deviation from the known path may rapidly lead to being totally lost. And the reason I chose that quote is that phrase, totally lost, and I think we can all think of students over time who have been totally lost, and the idea that has happened at some point because they don't have the number sense. According to Hibbert in 1999, the phrase number sense is often used to mean conceptual fluency, understanding place value and the relationships between operations. Children need to be both procedurally and conceptually fluent. They need to know both how and why. Children who engage in a lot of practice without understanding what they are doing often forget or remember incorrectly those procedures. Further, there is growing evidence that once students have memorized and practiced procedures without understanding, they have difficulty later to bring meaning to their work. So another definition for mathematical fluency from Enrich Maths: students exhibit computational fluency when they demonstrate flexibility in the computational methods they choose, understand and can explain these methods, and produce accurate answers efficiently. Russell in 2000 spells this out in more detail and suggests that fluency consists of three elements: efficiency, accuracy, and flexibility. Efficiency: this implies that children do not get bogged down in too many steps or lose track of their logic or strategy. An efficient strategy is one that the students can carry out easily, keeping track of sub-problems and making use of intermediate results to solve the problem. In the idyllic world, we would give students a problem and allow them to find their own solutions, and then compare all the different solutions that students have and decide collectively the most efficient and the most effective method. Accuracy depends on several aspects of the problem-solving process, among them careful recording, knowledge of number facts, and other important relationships and double-checking results. Teaching students to check their work, teaching them to set their work out in a mathematical way. These reduce problems and improve accuracy. And flexibility requires the knowledge of more than one approach to solving particular kinds of problems, such as two-digit multiplication. Students need to be flexible in order to choose an appropriate strategy for the numbers involved, and also be able to use one method to solve a problem and another method to check the results. So fluency demands more of students than memorizing a single procedure. They need to understand why they are doing what they are doing, and know when it is appropriate to use different methods. I've seen it taught, and I've even seen it written in textbooks, that to compare two fractions, we use a common denominator. In an example like this, it's very easy. In the primary national curriculum, students are expected to be mathematically fluent also, and it is directly mentioned that you should be able to compare fractions by looking at common numerators also. In this example, again, it's a little bit harder to see, but the idea, and again, pause if you want to have a think about it for a little bit longer and how you would explain it. But you can see that the first fraction is a quarter, and the second fraction must be a little bit more than a quarter. And in the final example, it's perhaps a little bit more abstract in how we can think about it. But if we look at these two numbers, almost instinctively, a mathematically fluent student will know which one is bigger. If you think of that on a number line, it's very clear where they lie and which one is higher up the number line. And I think part of developing mathematical fluency has to be by making connections and allowing things to become visual to try and get understanding. So the first example we can see very, very clearly by splitting it up into 17ths. perhaps by using a double number line. It does take some pre-preparation, but you can see here very clearly which one will be bigger. And again, for our final example, with a number line, you know 11 out of 37,238 is going to be very, very, very small. So intuition should enable those ones to be done very simply. But that kind of mathematical fluency and that type of problem solving should be included in our lessons where we are comparing fractions and looking at fractions. So I've taken another definition here from Richard Perring, who's part of the Maths Mastery Programme, and he says that having a method that always works is useful, but always having to use it isn't. Mathematical objects and operations are underpinned by different structures. By choosing a structure relevant to the problem, tasks which appear to require complex methods or procedures can sometimes be solved efficiently and accurately. Students should be aware of these structures and be given opportunities to look for and work with them in order that they can efficiently, accurately and flexibly solve problems. I think that is fluency. So there's a little quote there, and I think each of these definitions has something a little bit more to add to it. I'm not saying that one is better than another, but the idea of being able to move between mathematical thinkings and use manipulatives where needed and diagrams where needed, and to understand it, is part of mathematical fluency, and I think it's certainly a part of mathematical fluency that we can teach. Again, here is the slide I started my presentation off with, and I think this is such a lovely task because students, as soon as they can work out the area of a circle, can start to tackle this problem. Some students will, again, you could include your algebra in it, and you could start calling each length x of the square, and then each diameter and radius accordingly. But you can even take like an intuitive sense that comes that if we added more and more circles over time, it would become more and more pixelated, almost like a TV screen, until eventually it almost seemed like it filled the whole screen up. And again, here we're developing mathematical ideas of iteration and infinity. Capult in 1989 documented the need for and the benefits of representational fluency in maths. Graphs, tables, symbolic expressions, verbal expressions, diagrams, and interconnections between them. Some mathematical representations are mental and are hard or even impossible to put on paper and articulate. But we still need to take simple models that can help students, like graphs and bar models and cubes, and use them at the right time to try and develop mathematical understanding. So from the very famous Cockcroft report in 1982, there's a phrase here that I've underlined. Fluent performance is based on understanding of routine which is to be carried out. And it's also followed through with mechanical performance is performance by rote in which the necessary understanding is not present. Although mechanical performance may be successful in the short term, any route which is carried out in this way is much less likely to be capable of use in other situations or to be retained in long-term memory. In the pursuit of fluency and in the interest of developing the mathematician, there are very strong arguments in focusing on number early. In some schools, the Year 7 curriculum is almost exclusively focusing on number. but certainly not moving on to more abstract ideas and algebra until number is secure. Delaying calculator use until students are numerically fluent, and even then restricting it. There are very good reasons why in primary schools they tend not to use calculators at all, and those reasons should, for many students, continue into secondary school. Although they do need to be able to access and use technology, if that's at the expense of them developing mathematical fluency, then it's counterproductive. Coming back to the problem that we looked at earlier, there are many students who do GCSE who would type this into their calculator. There are many students also at A-level who would type it into a calculator. And they're losing the opportunity to access this maths, to use their maths brain, to make those connections. We must restrict calculator use only when it's appropriate. And schools and teachers do need to come up with a clear policy as to when it is and when it is not appropriate to use calculators. Simply allowing students to use them to appease a form of laziness or apathy isn't a good reason. It is right that some students will struggle to do numerical calculations without a calculator, and that's all the more reason for teaching using methods that they can understand. The type of number lines drawn below are very familiar in primary schools and very familiar to students in the first layers of teaching to try and make them fluent when it comes to number work. And if students come to secondary school and they are not fluent, that's all the more reason that we should continue to try and help them in that journey. This might be a good place to pause the video, because there's some absolutely wonderful questions here that would probably take 5 to 10 minutes to have a really good think about. All of these are number problems, and they're to be done without a calculator. I used this exact activity with my Year 12 class a few weeks ago to try and deepen their ideas of algebra, and also to show them how rewarding and wonderful number use is. So many students were doing the most simple calculations using their calculator and losing that opportunity. This was actually a resource designed for Year 6 students in Shanghai, and it's notable the curriculum there isn't differentiated. So this would be an expectation that all students were accessing this type of maths and really developing that number. And if you pick any one of these questions, you can really see why the algebra that will later follow from being really proficient at this will be there. Pick question D, for example. 79 lots of 1.25. Add 1 lot of 1.25 is 80 lots of 1.25. And then making that the calculation. NCETM, the Maths Mastery Programme, has invested an awful lot of money in making resources to try and address that idea of fluency. The resource here, I think, is an absolutely wonderful resource in that it makes students think, it makes them reason, and it's actually designed as an assessment so that teachers can see, is a student really fluent in their understanding of multiplication, or are they just able to apply an algorithm? Here's a lovely resource from the Enrich website. Again, I think it really hits that idea of developing mathematical fluency. Obviously, it's building to ideas like highest common factor, and perhaps this is something that could be used before then to try and really gain that understanding, so that when the topic is formally taught with perhaps algorithmic methods that the school might use, it's understood rather than just being a system that's put in place for no apparent reason. Enrich suggests 3 things that can be put in place to help students develop mathematical fluency. Manipulatives. We learn by moving from the concrete to the abstract, and structured apparatus such as deans, graphs or bar models can be helpful. However, the meaning isn't the manipulatives themselves. It has to be constructed by the children over a period of time, through playing around with them and connecting them directly to mental and recorded calculation. I really believe that strongly, that the meaning of manipulatives isn't that the manipulatives in themselves are for students to solve problems. The manipulatives help students understand problems, and if they understand problems, they're more likely to be able to solve them. But they're also more likely to be able to understand and become fluent in maths. Talking about their work. It is often said that you can't do maths unless you talk maths. But the quality of the talk is important. It is not simply children sharing how they did a particular calculation, but describing why and how it worked, and how their method is the same or different to those of others. In other words, giving children opportunities to use those higher level skills by comparing, explaining and justifying. Russell says, the reason that one problem can be solved in multiple ways is that mathematics does not consist of isolated rules, but connected ideas. I think that idea of talking about their work can be seen in the lesson as the teacher rotates round, but also seen through the questioning and the skill of the teacher. And those are things to be developed, and those are things that will help students to develop mathematical fluency, asking that question, why? Why? Why have you done it that way? Is there a better way of doing it? And finally, consolidation in meaningful contexts. By offering children practice in context, we help them to make links between types of situations that a particular strategy might suit. Russell calls this mathematical memory, which is different from just memorizing. Russell says that important mathematical procedures cannot be forgotten over the summer, because they are based in a web of connected ideas about fundamental mathematical relationships. And again, coming back to why mathematical fluency is important, is that if students just learn things and learn them by rote, they will forget them. They will forget them, and that is the bane of all of our lives as teachers, is we teach one thing and then 1 week, 1 month, 1 year later it's gone. If we can develop mathematical fluency, that won't be the case. To Mark McCourt, who wrote the Teaching for Mastery book, an effective mathematics education system is one that focuses on teaching approaches that maximize subsequent progression rather than pursuit of short-term, superficial successes. I think we've all been guilty at some point, maybe often, of looking at outcomes in year 11, outcomes in year 13 as being the be-all and end-all of our teaching lives. And teaching for mastery really is always about teaching for the next stage, teaching for the next progression in someone's life. And the idea that maybe teaching in year 11, making students all the more suited to doing A-level, or perhaps students doing A-level, making them suited to go on into life or go on into university with whatever they choose to study. We're always, or quite often, looking for short-term, superficial successes. Controversially, in the current climate of teaching and learning, and best teaching pedagogy, setting up an objective at the beginning of a lesson, then, under best practice informative assessment, seeing how many can do this cannot be used as the sole measure of an effective lesson. How many understand it rather than can do it? How many have made mathematical connections between topics? How many are flexible and efficient in their method? How many have moved beyond recall? How many are ready for the next, more complex stage in their learning? These are things that are hard to measure. The Maths Mastery Programme by NCETM puts fluency right at the top of its priorities. The purpose of my presentation today is not to advertise or to even deliver content from the Maths Mastery Programme, but I certainly think if you're more interested in developing ideas on fluency and getting resources which develop fluency, the Maths Mastery Programme is a good place to go to for this. So right at the beginning, I asked, what does it mean to be a mathematician? And I'm not sure what you thought or what you wrote, but the mathematician's main reason for existence is to solve problems, according to Halmos. When I was given exactly the same question at the beginning, how would you define mathematical fluency? I think it's a good place to end with what my response was, which I don't think is as thorough or as rigorous as many of the ones I've discussed, but I think it links to being a mathematician and links to solving problems. To be mathematically fluent is to be able to take sensible steps to explore both familiar and unfamiliar problems. I'd very much like any feedback and thoughts that anyone might have on fluency or anything that I've discussed. If you're interested in any of the resources that I've got, I could easily share those. This is presented by Ben Adams, and my email address is on the screen there. Thank you very much for listening.